Section 4. The Relational Model 1. Introduction. Up to this time, you have learned a lot about data models. In this study session, you will learn about one of the data models, the relational data model, and see how the ER diagram can be used to graphically represent this data model. As you learned earlier, the relational data model is widely used in most commercial DBMS, thus the need to understand it. In this study session, you should focus on the basic components of this data model and build upon that in the next sessions to understand how these components are involved in managing and accessing data in the databases. Organizational database systems. Learning outcomes. At the end of this study session, you should be able to explain the relational database model offers a logical view of data, discuss the impact of keys in relational databases and the different types used, explain integrity rules. Logical view of data. In your first study session, you learned that the DBMS manages and controls access to the data and the database structure, and that places the DBMS between the application and the database. The result of this flexibility of the DBMS, however, is a more complex physical structure. The database structures required by both the hierarchical and network database models often become complicated enough to diminish efficient database design. The relational data model, however, changed all of that by allowing the designer to focus on the logical representation of the data and its relationships rather than on the physical storage details. You could liken the relational data model to the automatic gearing system in automatic vehicles, which replaced the manual systems where you need to shift and adjust gears yourself. In essence, the relational model enables you to view data logically rather than physically, and it's much easier to understand than the hierarchical and network models. Logical simplicity tends to yield simple and effective database design methodologies, and the table plays a very important role in the relational model. Therefore, this discussion begins with an exploration of the details of table structure and contents, table structure and characteristics. The logical view of a relational database is based on relations. A relation is thought of as a table. A table as a two-dimensional structure composed of rows, records, or entity instances, aka tuples, and columns, attributes, or fields. It is essentially a group of related entities, entity set. You summarize in Table 4.1 the characteristics of a table. Table 4.1 Characteristics of a table. 1. A table is perceived as a two-dimensional structure composed of rows and columns. 2. Each table row tuple represents a single entity occurrence within the entity set. 3. Each table column represents an attribute and each column has a distinct name. 4. Each row column intersection represents a single data value. 5. All values in a column must conform to the same data format. 6. Each column has a specific range of values known as the attribute domain. 7. The order of the rows and columns is immaterial to the DBMS. 8. Each table must have an attribute or a combination of attributes that uniquely identifies each row. Figure 3.6 in your previous lesson is a good picture of the structure of a table, but you show a more detailed structure of a table in Figure 4.1 below. The figure shows the relation for a database entity student within the Tiny College database. Table name, student, database name, CH03, Tiny College, student number, student last name, student first name, student middle initial, student data of birth, credit hours earned, student classification, grade point average, student transferred from another institution, department code, 4-digit campus phone extension, number of the professor who is the student's advisor. Keys. To understand the concept of keys in relational database and their importance, consider the following example. It is believed that everyone offering CIS-201 is a student. However, you need to identify each student uniquely in order to properly record scores for each. Your unique identity as a student of this course is your matric number. Your matric number in this case is a key. Key is one of more attributes that determine other attributes. Determination in database term means if you know the value of attribute A, you can determine the value of attribute B. Thus, if you know your matric number, you can know your name and your score in CIS-201. Each row in a table must be uniquely identifiable, and this necessitates the selection of one or more of the table attributes as the key attribute. The principle of determination is very important because it is used in the definition of a central relational database. Concept known as functional dependence. The term functional dependence can be defined most easily this way. The attribute B is functionally dependent on A if A determines B. More precisely, the attribute B is functionally dependent on the attribute A if each value in column A determines 1 and only one value in column B. Using the contents of the student table in figure 4.1, it is appropriate to say that student phone is functionally dependent on student number. For example, the student number value 321452 determines the student phone value 2134. On the other hand, student number is not functionally dependent on student phone because the student phone value 2267 is associated with two student number values, 324274 and 324291. This could happen when roommates share a single landline phone number. Similarly, the student number value 324273 determines the student last name value Smith. But the student number value is not functionally dependent on student last name because more than one student may have the last name Smith. To learn the following definitions pertaining to keys, and you will use figure 4.1 to illustrate them. A composite key is composed of more than one attribute. A key attribute is any attribute that is part of a key. A super key is any key that uniquely identifies each row. A candidate key is a super key without unnecessary attributes. A primary key, PK, is a candidate key chosen to uniquely identify every row in a relation or to uniquely determine every other attribute in any given row. A secondary key is an attribute or a set of attributes which may not necessarily uniquely identify a row but are used strictly for data retrieval purposes. A foreign key, FK, is an attribute whose value matches primary key values in a related table. Foreign keys are used to enforce database referential integrity. A FK contains a value that refers to an existing valid row in another table relation. For instance, you could use the combination student number, student last name, student first name, student initial as a key for the table. This combination is a composite key. Each attribute in the combination is a key attribute. On the other hand, you could decide to use the combination student last name, student first name, student initial, or student last name, student first name, student initial, student phone as the key of the relation. Assume a student's mother decides to check up her child's performance in school. She is not expected to know her child's student number, but she definitely knows his surname, student last name, and this could be used to check up several students who possibly share the same surname. Then it will be easier for her to identify her own child. That is the essence of a secondary key. Each of these three composite keys can be referred to as a super key if it uniquely identifies a row. However, a careful look at the first composite key reveals that student number is alone sufficient to identify a student without all the other attributes. Student number is therefore a candidate key in this regard. Since the student number can uniquely identify any given row in this relation, it could be chosen as a primary key, while either the student last name or student first name could be used a secondary key. There are still more things to know about keys. Keys should not be null. A null means no data entry for a particular attribute or field. This is not the same as entry a blank or space because a blank space is itself a character. As much as possible, nulls should be avoided in other attributes, while they must not be allowed in primary keys. Nulls could represent an unknown attribute value, a known but missing attribute value, or a not applicable condition. An example of this is seen in the student initial field of your student table in figure 4.1, which is empty for the student with STUNUM is equal to 324258 because it doesn't have an initial, an example of a not applicable condition. Nulls should be avoided as much as possible because they can create problems when functions such as count, average, and sum are used, and can also create logical problems when relational tables are linked. Relational tables are linked by their columns. Relational databases employ what is called control redundancy through the use of keys to create relationships between tables as shown in figure 4.2. Tables within the database share common attributes, and these attributes enable such tables to be linked together. In this regard, multiple occurrences of values in a table is not redundant since it is required to make the relationship work. Redundancy exists only when there is unnecessary duplication of attribute values. Data redundancy leads to data anomalies and can destroy the effectiveness of the database. Foreign keys are used by relational databases to control data redundancy by using common attributes shared by tables and are crucial to exercising data redundancy control. Sometimes, data redundancy is necessary, and this is one such case. Integrity rules. Integrity rules are meant to ensure data integrity in the database. Many RDBMS enforce integrity rules automatically. However, it is safer to ensure that your design conforms to entity and referential integrity rules summarized in Table 4.2 below. Note that instead of allowing null attribute values, you should use flags to indicate the absence of an attribute values. Entity integrity. Description. Requirement. All primary key entries are unique and no part of a primary key may be null. Purpose. Each row will have a unique identity and foreign key values can properly reference primary key values. Example. No invoice can have a duplicate number, nor can it be null. In short, all invoices are uniquely identified by their invoice number. Reference integrity. Description. Requirement. A foreign key may have either a null entry as long as it is not a part of its table's primary key, or an entry that matches the primary key value in a table to which it is related. Every non-null foreign key value must reference an existing primary key value. Purpose. It is possible for an attribute not to have a corresponding value, but it will be impossible to have an invalid entry. The enforcement of the referential integrity rule makes it impossible to delete a row in one table whose primary key has mandatory matching foreign key values in another table. Example. A customer might not yet have an assigned sales representative number, but it will be impossible to have an invalid sales representative number. Integrity rules are needed to inform the DBMS about certain constraints in the real world. Specific integrity rules apply to one specific database. Example, path weight must be greater than 0. General integrity rules apply to all databases. Two general rules will be discussed to deal with primary keys and foreign keys. primary keys. Primary key is a unique identifier for a relation. There could be several candidate keys as long as they satisfy two properties: uniqueness, minimality. From the set of candidate keys, one is chosen to be the primary key. The others become alternate keys. Example: the relation R has several candidate keys: ID, SSN, license number, name. If we select ID to be the primary key, then the other candidate keys become alternate keys. The entity integrity rule. No component of the primary key of a base relation is allowed to accept nulls. What are nulls? Null may mean property does not apply. For example, the supplier may be a country, in which case the attribute city has a null value because such property does not apply. Null may mean value is unknown. For example, if the supplier is a person, then a null value for city attribute means we do not know the location of the supplier. Nulls cannot be in primary keys, but can be in alternate keys. Example: SSN may be null for one and only one person. Why? Foreign keys. A foreign key is an attribute of one relation R2 whose values are required to match those of the primary key of some other relation R1. R1 and R2 can be identical in bracket. Example: SP relation has attributed S hash and S relation has primary key S hash. Then S hash in SP is considered a foreign key. SP is called the referencing relation. S is called the referenced relation. We can draw a referential diagram: SP to S hash to S, or simply SP to S.